All right, let's take a look at our second problem in Unit 5. So here we had a distribution of data, and we just had a histogram, okay, that they had collected. They did tell us that the mean of this has an actual is actually at 403, and the standard deviation of it is at 278. So let's see here. So this is this the population? Shows the distribution of houses in a certain city. So I guess that these are the population amounts, okay? The population mean and the population standard deviation, okay? Because it's important, again, you have to always enter into a situation. Is this population information or is this for a sample? Okay, we've always got to keep those two things straight. All right, so here we have it. Wasn't told it was a sample, so I'm going with that it was the population. So then here we have this, and we want to estimate that probability that the house was less than $500,000. So that's this location here. So I just had to total up that percent and that percent, and that would be the percent of houses that are less than 500,000. So I just added those two bars together, 0.34, and I estimated 0.37. You know, if you're pretty close to that, then if you had put 0.36, you know, that'd be fine. So it's essentially correct if you give a total between this and this. So they were giving you, see, that leeway on what those numbers could have been so that they were approximate, and shows the work for that sum of those first two bars. Okay? All right, next. Now, look here. Now we have a sample of 40 houses. See? So we have to keep those items straight. Okay? If we have that sample of 40 houses, then what's the probability that we get a sample's average, that the average of those 40 houses will be less than 500,000? So what we have now is something different. We have got now, let me show you the difference between what's happening. We had that previous picture that was the population, and it was that skewed right distribution right here, okay? But what the deal is if we take samples of size 40, and we're talking about means here, so let's think, you know, random and independent, one house independent of the other, and that kind of thing, large enough. What is large enough for means? Central limit theorem says it has to be n has to be greater than or equal to 30. So even though this population is skewed to the right, central limit theorem says that if n is large enough, which 40 is large enough, then our distribution of samples, okay, so that's an average of 40 houses, that's an average of 40 houses, that's an average of 40 randomly selected houses, and so on. So this is a sampling distribution for samples of 40 houses, okay? So I then have got the approximately normal model to apply because of the central limit theorem. All right, so the question is asking us, what's the probability that we will find one that is less than 500,000? Okay, so because of that, because our sample size is 40, and then we would have the approximately normal model. Okay, so our distribution of those samples is approximately normal. Then I can do normal model math using that population mean of 403,000 and that population standard deviation of 278,000. Now, keep in mind this right here. See this formula chart for the sampling distributions? So let me zoom in here and let's take a look at what we're talking about. We do not have proportion information. We have means, okay? So look at this right here. The mean of all of those X bars, the mean of all those samples will be centered at the population mean. So that's telling me this, that the center of all of these X bars, The mean of all of these X bars is going to be centered at the population mean of 403,000. Okay? All right? But then remember how when n is getting bigger, so if we have this variability of the population here, the variability of this population is 278,000. But when we have this, we're going to have less variability. Well, how much less variability? The standard deviation for these X bars is whatever that population standard deviation is divided by the square root of n. Okay, and that is right here. So that means that whenever I take that 278,000 and I'm going to be dividing it by the square root of 40, then that's how much more compact it is. That's how much less variability I have. So I have those numbers here. So see, look, our sampling distribution is centered here. Our sampling distribution has this standard deviation of 43,000. See, much lower, much less variability. All right, so then I do my z-score and all that kind of stuff. So I've got this. Now, my thought was, why am I doing z-scores? Okay, and not t-scores? Because who's got a mean test? T, not z. But remember, for means, you're using t-scores because you only had the sample standard deviation, and that's not what we have here. What we do have the population standard deviation. So this is kind of interesting here. So because we happen to have that population standard deviation, then I'm able to do z-score stuff and not just more variability with t-scores. So how much was the probability? It's 500,000 or less. So see, I'm asking $500,000. Oh wait, did it say less or greater? Let me see here. It said, oh, it says less. Okay, so we're going to have quite a bit of area that is less than 500,000. Okay, and so here we have a z-score of 2.21, and that made 98.6% of all the homes being less than 500,000. Now, where our population, when we had done that here, that was an estimate of 71%. So interesting, 98.6%. Now, the catch here is that this here, let's keep in mind, population versus sampling distribution. This says 71% of all homes have sold for 500,000 or less. Individual pieces of data, individual homes. Okay, but this is not talking about individual homes. This is talking about an average of 40 homes. So average that 40 homes, and let's see what proportion of all of the averages of 40 homes are less than 500,000. So it was a lot more, okay, because it took a lot to get a whole average higher than 500,000. All right, so there's that. Indicates that you can use the normal, has the correct mean and the correct standard deviation. Indicates that correct boundary of that 500,000 or less, and includes that probability correct based on the numbers you used. All right, next, here we know. So now we have this situation where they do an estimator. They say, hey, let's see, maybe we could, let's make this easier. Let's say we do this estimator for this thing called a sample mid-range. Okay, a sample mid-range. And they're going to use this formula right here. Sample mid-range. Take the min, take the max, add them, and divide by 2. So they're like averaging the mid and the min and the max. Well, I personally would be afraid to do that because you're probably going to have some upper outliers. In fact, look at this one. This one looks like an upper outlier. Okay, so is that a really good estimator? I don't know, because that's going to impact that mid-range quite a bit. All right, so the question just says calculate the sample mid-range. So can you understand what's going on and use that formula? Okay, so I just use a formula. I take this 1.084 million and this 34,000, add them and divide by 2. Okay, and so then the sample mid-range was 559. All right, now this sample mid-range is much easier to calculate than taking a mean and getting the mean of that sample because it's only 2 values. So explain why that is maybe a preferred method. Well, because I don't have to get a whole bunch of samples and get all of those samples means. I just take 2 values. Okay? I just take 2 values and then I just find the average of those 2 values. All right, so correct to get the full credit, you had to actually do the correct computing and then say it's easier to calculate because, and let's see, and then it just says give a plausible reason of why the mid-range is compared. All right, next. Now, here's where it gets interesting. So what they do is they actually run a simulation. They take samples, okay, they take 100 random samples of houses, let's see, set 40, sample size 40. So they do that same thing that they did here. They took a sample of 40 houses and then got the mid-range for a sample of 40. So they did a sample of 40, calculated the mid-range, and then that's what each one of those dots is. So that right there came from 40 houses and the sample mid-range calculations. The minimum and the max divided by 2 gave you that point right there. This point right here came from 40 homes, a random sample of 40 homes. Take the min, take the max, add them up, divide by 2. That's the sample mid-range. Okay. So they then took all of these sample mid-ranges to see where that was. And based on these results, holy moly, the mean of all of these 100 was 617 with a standard deviation of 136. Whew. So crazy. So what happened, the question then is, based on these results, explain why the sample mean, just a regular old X bar of 40 houses, might be better than taking 2 of just the mid-range, taking a min and max and adding them and divide by 2. Why would the entire average of 40 be preferred than min and max divided by 2? So here's what I wrote. Okay, so first of all, let's think about this. This one gives a mean at 617. And what's the original mean? The original mean of the population was 403,000. Okay, the original standard deviation of the population was 278,000, I think. Okay, all right. So yeah, it was a little less variability. But hello, this center was not even close to that right there. Not even close. Okay? All right. So that's what I started off with. Since the mean of this sampling distribution, this is called the sampling distribution of these sample mid-ranges, is 617,000. That is very far off from that population mean and the mean of the sampling distributions of the sample means, okay? Because that, we know, because look at this right here. All of the X bars, if you take a whole bunch of X bars, they should center at 403,000, okay? So that sample mid-range is way off. All right, furthermore, let's look at the standard deviations. The standard deviation for this one is 136,000. That's quite varied as compared to what was the standard deviation for these X bars of 40. It was that 43,956. So if you compare two sampling distributions, this one made up of X bars averages of size 40 homes, averaging 40 homes, sample of 40, average all 40, as compared to just taking 40 and not averaging all 40, but taking 40 and just doing the min and getting the average of the min and the max. Okay, do you see how getting an average of the min and the max could just really throw things off? Okay, so that is shown in our numbers here. It had much larger variability as compared to that 43,956, much greater variability, and the mean was not even centered in the right place. So just overall, not good. So here's how you could get full credit on this one. Essentially correct if you state that this sample mid-range is a biased estimator. So they're saying that your results, see, they're going to be pulled in the direction of the skew. And remember how we know the population is skewed right. See, so this mid-range is going to be very affected by those upper outliers. So that's why it was so biased towards those right skewed items. Okay, and it provides numerical evidence. So you had to give that actual number value for the center. So they actually said you can get an E if you just argued about the center. You could also get an E if you just argued about how the variability of it is less precise. So you didn't actually have to do both. So that's interesting. Or, let's see, they said the shape of this one is not approximately normal. Okay, so that was also a flaw. And think about it. What size samples are these? These are made from samples of size 2. Each one of these actually came from 2 houses, right? So isn't that from 2 houses not going to fix the skew of the population? So you could say the shape is not approximately normal, and so on. So there's quite a few different ways that you could have that criteria to get an E for that. But the key was just really understanding the difference between population, the standard deviation or the sampling distribution. It's all vocabulary. This sampling distribution for these X bars that were made from samples of size 40, they averaged all 40 items, versus this, which essentially averaged 2 items. Okay? It averaged 2 items together. Anyway, so there you go. All right. Understanding all of those is really important. So I hope that helped you kind of get some of those things straight on sampling distributions.